toggling stop. That means this red LED, the second interrupt has a highest priority. So whenever the high priority interrupt get serviced, that means when it does what it has to do, then the first interrupt which has a lower priority gets stopped. But the moment I stop the high priority interrupt, you can see back again, your first LED starts blinking again, right? Is it amazing? Let me show you one more demo. How this is really funny thing. Let me reset my nuclear board. So here's a reset button. And now you see the both LEDs stop now blinking. So what I'm going to do is I'm going to press both button at the same time. Okay, so what then happens is I'm firing two interrupt at the same time. So let me press the both button here and see what happens. So when I press the both button, believe me, I press the both button. You see the high priority interrupt because it has a highest priority. It is executing, so the red LED is blinking. But even though I pressed the first button as well, it didn't blink the green LED. But the moment I stop the high priority interrupt, look at this. Oh, when I stop, I think it didn't press, but you can see it's blinking because this is stop. So high priority interrupt when I stop, when I start, high priority interrupt, you look at this blinking stop, right? I hope this gets through what I mean, right? Let me reset again just to show you because this is very interesting. So I press the both buttons, so both interrupt get fired. And now you see the LED is blinking, red LED, which has the highest priority. The moment I stop the high priority interrupt, oh, I think this button has a deep bounce maybe. Let me reset again. Let me fire both interrupt. Okay, and this first interrupt is servicing high priority interrupt when I stop. Now you see it resumes, right? That means I press the first button as well, right? So I hope this demonstrates the capability of an interrupt. So this is what we will going to implement today. So we are not just configuring the external interrupt, a multiple external interrupt with the two button switches as an input, but we will also demonstrate how the priority impacts the execution of an interrupt. Okay, so this is the demonstration that I wanted to show you. Now let's go back to slides and then I'm going to take you through the entire journey and the process. And I hope you can see my screen. And I hope you see my slides. I don't know.
Yep, we do.
Okay, all right. So now I showed you the demo. Let's see how this can be achieved. Okay. So today we will be exploring how to use multiple interrupts and how to set the priorities into the Cortex-M microcontroller architecture. And the microcontroller that we will be using is the STM32F4 microcontroller. So we will first look at the overview and then we will see how to implement the interrupt. We have seen this into the previous engineering hour episode, but I want to lay down the foundation so it will put things in a perspective. Then we will talk about multiple external interrupt, how it works in the real action. Then we'll explore some key concepts that are related to the interrupt, especially an external interrupt. That's an interrupt life cycle. Then interrupt levels. There are different interrupt levels, and there is a concept called re-entrancy. So we're going to discuss all these things. Then we will explore interrupt priority and pending bit. So we just have seen the demonstration about it. So priority is very important, especially when you have a multiple interrupt. If you are just using one external or maybe just a one interrupt, then it doesn't matter that what you have to do first and what you have to do second, because you just have one interrupt. But for multiple interrupt, it's very important you should know the priority, how to set the priority. And then we'll look into the ST's HAL function, because ST gives us HAL API that has to deal with the NVIC controller. We have seen NVIC controller in detail. So to access the NVIC controller, we will be using the ST's HAL API, and I'm going to show you some of the key APIs that we will be using into this projects. And then we will be taking a project here where I'm going to show you implementing two external interrupt with the different priority. And then towards the end of the session, we will take the questions if you have any. If we run out of time, then feel free to drop your question into the Discord server. So the question is how to implement the interrupt. Of course, the information that you need can be found into the datasheet and the reference manual. But the key thing that you have to look into the datasheet and documentation is the vector table layout. And we have seen that the vector table layout basically have all the information. That means the priority and the number of an interrupt service routine and what address the interrupt service routine is. So all this information can be found under the vector table. So we have to look out for the vector table layout. And then we have to deal with an interrupt controller. And what we have to do first is we have to know how to enable or disable the interrupt. So the first step is whenever you want to use any interrupt into the microcontroller, you have to know how to enable or disable the interrupt. Once you know how to enable the interrupt, then we must know how to manage the priorities. Because I spoke about it, like if you are dealing with multiple interrupts, then because there are multiple interrupts, you have to write into the code that which interrupt, which process, which action is more critical and more important, so it has the highest priority. So we have to manage those priorities into the code. And then we have to know how to manipulate the pending bit. This is very important. The pending bit is basically responsible to activate the interrupt. Only if you just use the external interrupt or maybe just an interrupt, if you enable the interrupt, it's not enough. You have to activate the interrupt in order to get the interrupt do certain task, right? So this is how we will going to implement the interrupt into the microcontroller firmware. First, we enable and disable the interrupt. Then we manage the priorities of the multiple interrupts. Then we have to manipulate the pending bit. And finally, we also have to know that the CMSIS function, because interrupt in the microcontroller, especially let's talk about the ST microcontroller, you will going to set the interrupt at the NVIC level and the HAL level. Okay, you can also call the peripheral level, because the objective of the HAL API is to give us an access to the peripherals, right? So you can say whether it's a HAL level or maybe a peripheral level. Okay, so CMSIS NVIC level, to access the NVIC controller and the NVIC capabilities, we will be using the CMSIS functions, and we'll get into that bit later. So let's move on. So let's just understand how the multiple interrupt gets into the action. So let's say we have a CPU core here, and the CPU is executing a block of code that's a code A, and code A could be just considered as a main function because the code that execute is basically starts with the main function. So the CPU is executing a code A. So let's say the first interrupt get fired, and the first interrupt could be an EXTI0 interrupt. So when the first interrupt get fired, then the code A will gonna process the external interrupt request. EXTI0 interrupt request will get served, and it will toggle the green LED. Okay, so the first interrupt get fired and it will toggle the green LED. Let's say the second interrupt get fired, and the second interrupt is EXTI, let's say 15 down to 10 IRQ interrupt request. If the second interrupt get fired into the CPU core, the code A is going to service another interrupt that's an EXTI 15 down to 10 interrupt request, and that basically toggle the red LED. Okay, now this red LED starts toggling, so the red LED is blinking. That's what we have seen even in a live demo. So when the red LED is blinking, the green LED stops blinking. Okay, now you might ask the question like, why both LED is not blinking simultaneously? Wherein now, because you press first the EXTI0, so you fire the first interrupt, then you fire the second interrupt. The reason the red LED keeps blinking and the green LED doesn't blink, because the red LED has a high priority. So the high priority interrupt get executed, so it will keep executing. The moment you fire the second interrupt again, okay, then this red LED stops blinking and the code execution will be resumed and your green LED starts blinking. Now, I think you have understood how the two interrupt get fired into the CPU and how two requests been served by two different external interrupt request. Okay, IRQ handlers. So this is how we will going to implement the algorithm into the code that we will going to write. Now let's just understand the relation between a GPIO pin, because we will be connecting a switches to fire an external interrupt from the GPIO pin. So we will be connecting the tactile switches to the GPIO pin. And then we have to see how they connect to the NVIC controller. So you see, as soon as we fire the first interrupt, that's an external interrupt 0 get fired. So this EXTI0 interrupt request will be served into the CPU core, because we will have to write these 2 lines of code. And we just have seen in the previous slide that when we write HAL NVIC enable IRQ, so here we are enabling the interrupt. So when we call this function like HAL NVIC enable IRQ, that means we are enabling the external interrupt 0, EXTI0 we want to enable. And then all of a sudden quickly we call this another function HAL NVIC set priority, and we set the priority for the external interrupt 0 as number 8. So we are setting up the priority of the first interrupt as 8, and the 0 is basically a sub priority. So we are not dealing with the sub priority concept here. That's pretty more advanced, but let's just stay the discussion to just the priority. Okay, so the first interrupt EXTI0 get fired because we add these 2 lines of code, and this will come from this PA0 pin, because that's where we will going to connect the first button switch. And this PA0 will get connected to EXTI0 IRQ, and then this will get fired and this will be processed through the code. So let's say for the second button, I chosen PC13 pin, and PC13 comes between EXTI10 down to 15. So this blue interrupt get fired, EXTI1510 IRQ. So as soon as this external interrupt 13, EXTI13 get fired, we have to write this 2 lines of code, because by writing this NVIC enable, we are enabling the EXTI13. I'm saying 13, but it's written 15 down to 10, but it's the same thing. Okay, because the external interrupt 13 belongs to the same vector, right? EXTI15 down to 10. And to set the priority for the second switch, which is connected to PC13 pin, I'm going to set the priority 7. Okay, that's why I said that whenever we press the second button for the red LED to toggle, it has the highest priority. But then you argue with me that you would say, okay, why? Because here you wrote the number 7. So logically, if you look at the numbers, then you would say the first interrupt has a higher priority. But that's not how the priority works. In the interrupt priorities into the microcontroller, the lower is the number, higher is the priority. Because the second interrupt has a lower number, 7, than 8, the second interrupt has a higher priority. I hope this makes sense. If it doesn't make sense, just don't worry. We'll get into that in a future slides. But I think right now you know how the PA0 pin, GPIO pin, that's where the switch is connected to process the EXTI0 interrupt. That's the first interrupt. And PC13 pin will process the second interrupt, that's EXTI15 down to 10 interrupt request. Okay, let's go ahead. Now you might wonder and ask, because last time when we have done the basics of the interrupts, somebody asked the question like, Umesh, how much time it take to process the interrupt, right? So maybe that question will be answered here. So we will have to look the mechanism used by IRQ handler to process the interrupt request. Okay, so I already said the interrupt operates in the NVIC level, that means at the application level, and the HAL level. Okay, there are 2 levels on which the interrupt will be configured. So let's say when you fire the interrupt, then this EXTI1510 IRQ handler will get fired. So this function will get fired, and this function is a part of the CMSIS API core from the ARM company. So it's a part of CMSIS APIs. So as soon as this interrupt handler get fired, what happens is this will send the call to this function. So this function HAL GPIO EXTI interrupt request IRQ handler is a part of the HAL ST's HAL API. That's why HAL is added next to the function. So what I'm trying to make my point is, as soon as the interrupt get fired, it will send a request to this function, external interrupt handler, IRQ handler, and this function again sends a request to another function, that's a hel GPIO exti callback. So this exti callback function will get invoked, right? So when we write a microcontroller firmware, when we do all the settings into the IOC file, probably we write our user program and logic into this hel GPIO exti callback function. And many times we don't even see behind this function, this API, because this API exists because of this function, and this function get invoked from this function. But this is the process how the interrupt IRQ handler will be processed. So this is the way IRQ handler services the interrupt service routine into the microcontroller. I know this is a little bit crazy, boring, but remember this picture properly. I will going to show you into the real code how they are related. Okay, so this is the mechanism. Now you might wonder, okay, what about priority? Because we took two external interrupt, EXTI0 and EXTI13, we connected two switches, but where have we set the priority, and then how the priority works? So you can see on my slide, I have two interrupts. So this is an interrupt A and this is for interrupt B. Okay, and you can see this green part of this interrupt. So this green is basically an active interrupt, and this gray color is basically a part of inactive interrupt. So what I'm trying to show here is whenever the interrupt is active, so let's talk about this interrupt A. Okay, whenever this interrupt A get fired, let me just show you first the priority that we set. So interrupt A has the priority 8 set by us, and the interrupt B has a priority 7. That means the interrupt A has a lower priority and B has a higher priority, because the B has a lower priority number, and we talk about it. Lower is the number, higher is the priority. So whenever this interrupt get executed, the interrupt A get executed. So it execute the code execution, but then as soon as the interrupt B will get activated, when the interrupt B get activated, the interrupt A goes into inactive mode. Okay, so interrupt A is not operating. Let's look at this T1 clock cycle. At the T1 clock cycle, interrupt B gets activated, and at T0, interrupt B was inactive, right? So it doesn't exist here. So it started basically at T1. So as soon as the high priority interrupt gets activated, the low priority interrupt get inactivated, and the high priority interrupt does what it has to do. I mean, whatever you write into the code, and once it finish, then the code come back to the low priority interrupt. That's an interrupt A, and that's why at T6 your interrupt A resume its operation, right? So what we learn out of this picture is the high priority interrupt will be executed first, and the low priority interrupt will be inactive at the time. Okay, and you can, it's not what you can say, it's the interrupt A will be queued and interrupt B is executing, but you can just understand in a way that the A deactivated because it's inactive because the high priority interrupt is processing, right? And the question that is asked last time, like how much time it takes to service the interrupt servicing, right? And let me take you to the previous slide here. You can see if this is a T1, T0, T1, T2, T3, and it goes up to, let's say, T7. So if it's a T1, then it's a 1, 2, 3, 4, 5, and 6. So 6 clock cycle it will take. Even if you look at this picture, so this interrupt B takes from T1 to T6. So it takes the 6 clock cycle. Now, how much time this interrupt B will take to process depends on what frequency your microcontroller is operating on, right? And then you can calculate the clock, and from the clock you can calculate. Now, don't take this slide as a reference point for calculating, because I have shown here 6 clock cycle it takes, but in the Cortex-M microcontroller, it takes somewhere between 10 clock cycle to 15 clock cycle in order to process the interrupt. I hope this answers the question, but and at the same time, the concept of an priority. Okay, so the priority allow us to tell which interrupt has to execute first. Okay, now let's just talk about what is a pending bit. Okay, and again on the slide here we have again two interrupts. So here's an interrupt A and here is an interrupt B. And you can see here are some signs to make this picture more readable here. And here is a clock cycle. It starts from T0 and go all the way to T6. Okay, so let's say the interrupt A get fired. The star is basically to start, means firing the interrupt. So the interrupt A get fired and the pending state is cleared. So this yellow plus sign is basically says, okay, the pending bit is getting cleared. So now A starts executing and executing till the T3 cycles. Okay, now at T1 the interrupt B get fired. Look at the star here, but it is not executing because here the pending bit is not cleared. Okay, the pending bit get cleared for the high priority interrupt at T3 cycle. So at T3 cycle, actually your interrupt B starts executing. That's what my point was. If you enable the interrupt, but if your interrupt is not active, but then the question is, how will you activate your interrupt? You will activate your interrupt by clearing the pending bit, because when you clear the pending bit, that is where your interrupt comes into the action. I hope this makes sense. It's a little bit complex and a little bit relative how you see things, but this picture a little bit tells you how, what is a pending. So interrupt is a pending, and here this interrupt is because this pending state is cleared here. So here whenever the interrupt B is executing, it's a non-pending. So when it's a non-pending, not pending, that means the interrupt is executing. So interrupt is in active state. I hope this makes sense. The priority is to tell how important is to execute the more important task, the critical part of the code. And the pending bit is to tell the interrupt, okay, this is the time to activate the interrupt. Only enabling interrupt is not enough, right? That's what my point is. It's the process that you have to do, but when you activate the interrupt, when you clear the pending state, then only your interrupt get activated and then it starts functioning. So let's go to next line, next slide. And you can see here, there are some HAL APIs that's been given from ST to work with the interrupt, especially the NVIC controller. Now, as I said before, that the interrupt can be configured at the NVIC level and at the HAL level, means at the peripheral level. So when we are using this HAL API, that we are using the peripheral level, right, at the HAL level. And because ST gives us this API, HAL API, it reduces a lot of headache. So if you write the same code in the bare metal, then you literally have to go into register and flip every bit. And you should know everything about every register and every bit. And that's why you have to refer a lot into the datasheet. But if you use this API, they make your task very simple and very easy. Okay, so let's say if you want to enable certain interrupt, you would just call this function HAL NVIC enable IRQ. So it enable the interrupt request that you want to process. And if you use this another disable IRQ API, then it will disable the interrupt. Similarly, if you want to deal in your code with the pending bit, then you will use this API like NVIC get pending IRQ, set pending IRQ, clear pending IRQ. So these are the ready functions. These APIs will reduce a lot of headaches to deal with the interrupt. And then we have to activate and then set the priority. So we have this dedicated HAL NVIC get active and set priority API. And then again, one thing we haven't spoke about it, but because the interrupt in the Cortex-M microcontroller, Cortex-M4, basically because I'm using STM32F4 microcontroller, it gives you an ability to group the priorities, right? So you have an interrupt, you group, and you assigned the priority to the group. Okay, so you create a group of and then so you have a multiple interrupts, so you can assign the priority to the group of the interrupt. Okay, and that's very interesting because you can categorize them, create a different group, and classify them, and then execute. That's helps you write more better algorithm when you want to deal with very complex execution, code execution. But remember one thing, if you use Cortex M0 and 0 plus, M0 and M0 plus microcontroller, then you don't have this feature where you can have a priority grouping, right? So you don't have this capability in the Cortex-M. It's only for Cortex-M3, M4, M7, and M33. Okay. And by the way, if you there are so many HAL APIs, if you want to read about everything in very much detail, like what all the parameters are and what are all the API functions are, then ST has a dedicated document for it, HAL documentation. So you will get all the details. So these are just a few selected HAL API that has to deal with an NVIC controller or the interrupt. That's why I listed this, and I didn't want it to go to datasheet and show you, rather I prefer to put into the slide itself. So we will be using this API in our code. So look at this connection diagram. So the demo that I showed you, that inherits to this circuit connections. So you can see here I have two LEDs. Okay, and let me just show you. So there are two LEDs and two switches here. So the first switch is connected to PA1 pin. Okay, and the LED is connected to PA0. Okay, and then you have a red LED that's connected to PA5 pin, and the another switch is connected to PC13. Okay, I think there is this will be a PA0 and this will be a PA1 because this will be an EXTI0 interrupt and this is EXTI13 interrupt. But I hope you get the point, like there are two switches that fire two external interrupt, and every switch has one LED to take the action. Okay, so this is the underlying circuit. I mean, this is the circuit that I showed you. This is the same circuit that I mean. Okay, so let me show you into the code how we can configure the external interrupt into these two switches in order to control the blinking of an LED. So let me take you to the Cube IDE, and you can see here we have an IOC file. So you can see we have configured the PC13 pin as an EXTI interrupt 13, and then we have configured the PA0 pin as an EXTI0, right? Let me just expand the system view, go to GPIO, and let me just take this. Let me expand. And let me just select PA0 pin. And now you see this shows a blinking. And it says this is an EXTI interrupt 0. That's where our first switch is connected to. Okay, that has to do with the green LED. And the green LED is connected to this PA1 pin. So when I select the PA1 pin, that's where the green LED is connected to. So if I select a PC13 pin, that's where the second switch is connected to, and this connected to PC13, and this PC13 would going to control the LED that is connected to PA5 pin. Basically on the nuclear board you have a built-in LED as well, but I have connected a red LED to this PA5 pin. So that's for the second interrupt. Okay, so now you might wonder, okay, we set the pins, GPIO pins, as an interrupt pin, but what about a priority? So we have to go to the NVIC option. So when we go to NVIC option, let me create a little bit of space here. And you can see that EXTI line 0, this is for EXTI 0 interrupt. That's for the first button for the green LED. You see we set the interrupt number 8. That's exactly what I wrote in my slides, if you remember. So EXTI0 interrupt has the priority 8, and EXTI13, so this is an EXTI13 has a priority 7 assigned. So here you can set the priority number. And here is a sub priority that we are not dealing with here, but if you want to have much finer control, you can even have a sub priority for much precise control. And just make sure that you tick this box here for SysTick time base. Otherwise, this code will not function. But anyways, once this is done, then you can generate the code. And as you generate the code, it will take you to your main.c file. So this is our main.c file. Okay. So this is our main.c file. And in the main.c file, you can see only what we are doing is we are initializing the GPIO initialization, because we are using all the 4 components that we have connected to the nuclear board. They are connected to the GPIO pin, right? So they are basically has to do with a GPIO. So the GPIO initialization has happened, and you can see the while loop is completely empty. And you remember last time I talked about it, whenever we use an external interrupt, if I expand the core and if I go to the source file, we have seen that we have this exti interrupt.c file get created. So if I take you inside this interrupt file, because this will be created by the IOC file, we don't have to create manually. And then you can see there will be 2 handlers here. If I scroll down, you can see this handler, this function is for the EXTI0, that is for the first interrupt. External interrupt 0 is our first interrupt. Whenever we press the first button, PA0 connected button, then this EXTI0 will be fired. And this EXTI0 interrupt request then will call to this function. Okay, this is a little bit crazy, but yeah. So this is for the EXTI0, and this is for the EXTI13 interrupt. There are 2 external interrupt, and for every external interrupt, we have this external interrupt request IRQ handler here. Okay, and then if you remember, if I select this API, this function here, if I right click and say open call hierarchy, you can see in the lower right corner, I'm trying to make a space a little bit for you to see. If I select the interrupt, you can see it is associated with this EXTI0 IRQ handler, right? So if I take this function, right click and say open declaration, and then it will take us to this function that's a weak function and callback function. Okay, so it will take to the callback function. This is really crazy difficult to understand, and I'm just trying my best to give you the context. This is what we spoke about, right? If you remember. So first, this EXTI1510 IRQ handler will be processed, and this will call to the HAL GPIO EXTI IRQ handler, and finally it get called to this callback function. And in the callback function, we write what we want this interrupt to do, right? So let me take back to the code again. Okay, so that's why in the main function, when we scroll down in the user code, we have only one function, that's an HAL EXTI callback, right? Because this callback function is executing, and here we write a block of code. Let me just create a little bit of space here. So what happens is when we press the EXTI0 button, whenever we fire the EXTI0 interrupt, this if block will get executed, and that basically toggle the LED connected to PA1 pin. Okay, so whenever we fire EXTI0, the PA1 will get executed, and this flag variable will change its status if in case we press the second button, that's an EXTI13 external interrupt 13. So if we fire the second interrupt, that's an external interrupt 13, then this block of code will execute, in which we toggle the LED connected to PA5 pin. That's the red LED. Okay, so this is for the green LED, and this is for the red LED. All right, and then you see, just to show you the toggling function, I added this delay function here. And if there are any expert out there who is watching this video, they would say, okay, this guy is crazy using the delay inside the ISR. I know you should not use the delay function, but this is the only way. By adding delay into this callback function, I can show you the demo that I have showed you, right? Otherwise, you would never ever somebody, at least I have not seen yet, people can able to show the actual, the priority functioning the way we have seen in the beginning, right? So I don't recommend people to write this kind of interrupt service routine. I mean, don't write delay function inside the ISR, but I just wanted to show the toggling mechanism. That's why I added this 100 millisecond delay. I hope this is acceptable across all the experts out there. But anyways, so this toggles the LED with 100 milliseconds. Okay, and when the second interrupt get fired, again 100 milliseconds, and it toggle the LED. Otherwise, the reason is, if I do not add this 100 millisecond delay, then you should know that this Nucleo board is operating on 16 megahertz clock. So in 1 second, the clock is ticking 16 millionth time. And remember, we are not using any timer or anything in this code. We are just using plain GPIO, that's it. So that's why if I do not use this delay, then I couldn't able to show you, because human cannot able to see this just a few milliseconds or maybe nanoseconds delay. All right, so let me upload the code and show you the functionality. Okay, let me build the code, and you can see there's a one warning, 0 error, and 1 warning, but if I rebuild the code, it will go away. It will be 0 error and 0 warning. It's because when I wrote the code, I wrote for the different Cube IDE version 1.6, and this is 1.7. So it's a 0 error, 0 warning. Let me run the code. Let me press the run button, and now the code is uploading. So you can see this RGB LED is blinking. It's changing its color. And I think now the code execution is done. So the code is uploaded. So let me show you again to prove the logic that we spoke about, right? So let me press the EXTI0 button. So that's the PA0 pin. That's where the switch is connected to. Let me press. And you see when I fire the first interrupt, which is a low priority interrupt, it toggle the green LED. I hope you can see on a camera. So when I press another button, which is a high priority interrupt, that's an EXTI13. So when I press the button, look at what happens. The second LED, the red LED, which has the highest priority, starts blinking. So it's toggling with 100 milliseconds delay. And the first LED stops blinking because it has a lower priority. But this LED is still blinking if I stop the high priority interrupt, because the first interrupt EXTI0 is still in the queue. Okay, it's in a queued. I don't know technically is it right to use queued, but it's not that real queue, it's an English queue. So let me just fire the interrupt again, and you see it resume back again. So this interrupt was in queued. So as soon as the high priority interrupt finish, it's working. When it's stop, then the low priority interrupt get executed. I hope this makes sense. And let me show you one more thing. Let me fire the high priority interrupt. Okay, and if the high priority interrupt is working, so it's in the active state, and if I press this button, like the low priority interrupt. Doesn't matter for rest of my life. If I keep pressing this button, this interrupt will not get fired. Okay, because the first button, this EXTI0, has a lower priority. That's why even if I fire this interrupt, it will not get activated until the high priority interrupt gets stopped. So this interrupt gets stopped, and now only this will be working, right? I hope this makes sense, and this is the best way I could able to show you the priority and the interrupt. Okay, so let me take you to the slides back again. Okay, and I want to talk a little bit more, and then probably we'll take the questions. There is something more that you should know when it comes to dealing with the interrupt priority and all other things, you know, like interrupt address, priority, types, and other things. So you can see these are the pictures that I have taken up from the datasheet, and this is very typical interrupt vector table. And you can see here some priorities. Look at this. This interrupt has a negative priority, right? So remember, it is possible that some interrupt might have a negative priority. And remember one more thing. The lower is the number, higher is the priority. That means this negative number interrupt has the highest priority, and these are the exceptions that processed by the CPU core. You can see, and these exceptions are basically reset, hard default, and other, you know, system related functionality. And one more interesting thing that you have to see into this picture here is this all three interrupts which are a negative priority numbers, these are fixed. The type of a priority is a fixed priority. That means whenever the user write a code and try to configure this interrupt, they could not able to change the priority of these interrupts because these are exceptions. Remember, we talk about the difference between the exceptions and interrupt, right? So interrupt is a type of exceptions in the world of the ARM architecture. But remember these things. But when we use a normal interrupt, normal external interrupt, right? Or internal or external interrupt, you can see these are settable interrupt. So user can able to set the priority of that interrupt. By the way, I have implemented in the code and explained. Let me show you how. So if I take you to the next slide, you can see here we have an external interrupt 0 to EXTI4. So EXTI0 down to 4. And we used EXTI0 interrupt. Remember, our first button for the green LED was connected to EXTI0. Because EXTI0 was a settable interrupt, so we can set the priority. That's why we were able to set the priority 8. Okay, if you remember in the code, we set the priority number 8 for this EXTI0. If this would have been a fixed priority, we could not able to change, right? And also, if I take further, you can see there's another interrupt that we have used, EXTI1510 IRQ. That's for EXTI13, the pin that is connected to PC13, the switch that is connected to PC13. So this interrupt is also having a settable priority. That's why we can able to set for EXTI13, we set the priority as number 7, if you remember, right? So the EXTI13 we set because that was a settable, so we can able to set. If it's a fixed priority, then we cannot able to change. I hope this give you much more details on how this is really complex topics, by the way. Let's summarize what we have seen so far. Okay, so enabling NVIC is done on NVIC level and peripheral level. This is, I think I repeat quite a few times, but it's very, very important. So whenever you are dealing with interrupt, that means you are dealing with NVIC controller, right? Interrupt is basically managed by NVIC controller, and NVIC controller, you can able to control it on the NVIC level configuration and the peripheral level. That's the HEL, ST's HEL API, using HEL API. So interrupt can be enable or disable. That means when we use an interrupt, we can able to enable or disable the interrupt. We can active and inactive the interrupt. So we can write in the code, okay, we enable the interrupt, let's get activated. It's something like I am here presenting this presentation, all right? I'm here sitting but saying nothing. So I'm actually here presenting, but because I'm not saying anything, that means I'm not active. So that's what it means. You enable, disable, active, inactive, and then pending and not pending, because we talk about it. If it's a pending, then the interrupt is not servicing, right? It's waiting. And not pending means the interrupt is servicing. That means the interrupt is active at this moment. It is doing what it has to do. And you should know that the Cortex-M3, 4, and 7, M4, M4, M7 architecture allow group and subgroup priorities. That's what I spoke once when we were having a setting into the IOC file. We can able to do this. These are very advanced, settings when you're dealing with interrupt. But remember this is not available for Cortex M0 and 0 plus. So if you use any ST's microcontroller which is M0 0 plus, then you can't use it. Then in Cortex M347 allows 16 level of priorities divided on groups and subgroups for configuration. So it's again it's the same thing, but on very much finer control that can allow you to achieve. So some fact about the interrupt, especially for the multiple external or internal interrupt. The list of interrupt can be found in the datasheet. So one way you can see is the datasheet, and the other place where you can find the details about your interrupts are into the startup file. Okay, so if you go to, if you expand the core section of your project pan, then there will be a startup file and you will see all the interrupt names there. So then you would know, okay, how many interrupt is supported by your microcontroller. So in my case, it's a STM32F4 46. And every microcontroller has different numbers of interrupt, because different microcontroller has, like, let's say some microcontroller has more IO pins, some has less IO pins. If there are less IO pin, how could it give you more external interrupt on the GPIO pin, right? So these are like few technical things, but you have to always check into your startup file or the data sheet. Then one more thing I repeat quite a few times, but it's very important. The lower is the priority number, higher is a priority. That's why for red LED blinking, so whenever the red LED is blinking, it has the highest priority, because we set it for 7 priority for the red LED, and for green LED we set the priority 8. So remember, the less is the number, higher is the priority. And it is possible to change priority of exceptions, assigning different number of codecs. I mean, this is basically a feature for advanced microcontroller which uses the Cortex M347 and M33 class of architecture from ARM. But what does this mean? This means you can change the priority of an exceptions as well, not only with the interrupts, right? And if you use advanced RTOS or something, then you can see the RTOS give you capability to change the priorities in a runtime, right? So these are like the advanced thing. That's why interrupt will be exploited into the RTOS. And that's where on the top of HAL API, you see the RTOS API will come. Then it could be any RTOS API, it could be and free or commercial RTOS, whatever. So, however, you have to remember all the time in practice, the number of interrupt input implemented in real microcontroller is far less. So when you hear this crazy numbers, like let's say some microcontroller support, let's say M33 microcontroller supports 400 interrupt or something, these are just the numbers, but you cannot use this many interrupts, by the way. Like sometimes people go crazy and say, oh, it's possible, but it's very complex to manage. And that's where people then try and develop the software layer and one layer of it is your RTOS, right? To make it easy to manage the task and interrupts and priorities and sub priorities and all this, advanced stuff. But basically, if you can able to write your code without using RTOS, because if you are not using RTOS, not commercial, even free RTOS, you keep the complexity less in your code, right? And your code size would also be smaller, and you have a direct access to the controller, right? So that's the advantage. Maybe we will speak someday into the office hours. So this is all about how you implement multiple external interrupt into the Cortex-M microcontroller. I hope you have learned something out of this session. This is really complex topic. I keep thinking what I could take the best example case, and I just come up with this one. Thank you very much for your time.